Hi, we are Team21 and we will be presenting on our IoT project, which is on automated urban farming. For components, we used M560 pluses and some sensors. For technologies, we used BLE, painless mesh, and MQTT. Here is a list of things that we will be talking about. Firstly, we will talk about the project overview. For our project, our main features are the sensors that are connected to the M560 pluses that read data like soil moisture level, light, and temperature, as well as humidity. There will also be an automatic activation of lights and an irrigation system when needed. We used Bluetooth Low Energy to transmit information since it uses low power communication, and painless mesh was used as it is fault tolerant. Also, Gravio was used for real-time data processing, and Mailgun was used for notifications. I will now pass my time on to Ariel.
Thank you, Tisha. I will now be talking about the hardware and software components. Starting with the hardware, our setup includes 8 M56C plus devices. To gather environmental data, we've incorporated 3 different types of sensors. First, we use the MH sensor series light sensor to monitor the presence of light. Second, the DHT11 sensor allows us to track temperature and humidity levels, providing vital data for environmental monitoring. Lastly, the gravity analog capacitive soil moisture sensor helps us measure soil moisture levels, which is particularly useful in smart agriculture solutions. Moving on to the software side, our project is powered by the Arduino IDE platform, which provides a flexible and user-friendly environment for programming our hardware components. For communication, we've chosen a blend of protocols to ensure robust and versatile connectivity. BLE or Bluetooth Low Energy offers efficient short-range communication, while MQTT facilitates lightweight messaging between devices. Painless mesh is used for creating a self-healing network among our devices, ensuring uninterrupted data flow even if some nodes go offline. Lastly, UART provides a reliable point-to-point communication channel. To visualize and interact with the data collected by our system, we employ Gravio Studio as a dashboard. Then it enables us to create a user-friendly interface to monitor and control our project's various aspects in real time. And for instant notifications, we've integrated Mailgun to send email alerts based on specific triggers or conditions, ensuring that important information is always at our fingertips. I will now pass my time on to Darren.
Thank you, Ariel. I will now be talking about how to set up the IoT devices. Here we demonstrate how we set up our sensors by connecting each of them to an M5 stick. Firstly, we set up our light sensor, connecting ground to ground, VCC to 3.3 volts, and digital output to GP26. Next, we set up our temperature sensor, connecting ground to ground, VCC to 5 volts, and digital output to GP26. Finally, we set up our moisture sensor, connecting ground to ground, VCC to 3.3, and analog output to GP36. To set up our solution, we start by flashing all the M5 sticks with the appropriate codes. We first turn on the various sensor nodes, which are also BLE servers. We then turn on 2 more nodes. One is a BLE client that connects to the BLE servers to collect data, and another is a painless mesh slave node that conveys the data collected to our central node through the painless mesh network. And we connect these 2 nodes together with jumper cables to allow for UART communication.
Thank you, Darren. I'll be showing how to connect the devices to the IoT platform. Next, we will be discussing the security implemented in our project. In the context of BLE communication, ensuring the security of data transmission is important, especially in scenarios where privacy and integrity are critical. One of the most effective methods to safeguard against potential eavesdroppers, such as man-in-the-middle attacks, is through the implementation of encryption algorithms. In the context of our project, the adoption of ZOR encryption for BLE servers and clients presents a robust solution to secure data transmission. ZOR encryption is a simple yet powerful encryption technique that operates on the principle of bitwise ZOR operation. It is an ideal choice for resource-constrained environments like BLE devices. The ZOR operation is performed between the plain text data and the secret key, resulting in ciphered text that is transmitted over BLE network. So how it works in our project is each server possesses a unique encryption key, and this key is crucial for encrypting and decrypting the transmitted data. For the painless mesh network, the devices would need to possess the correct network credentials before they can connect effectively, preventing unauthorized access and potential data breaches. The use of Wi-Fi with a username and password for MQTT connections adds another layer of security. This setup requires that both the MQTT broker and the clients authenticate with the Wi-Fi network before they can establish a connection. And lastly, Gravio Studio's account protection and registration required further enhances the security of our data visualization and management processes. By requiring users to register and log in to access Gravio Studio, we ensure that only authorized individuals can view and interact with the data. Next will be our IoT project in action. Hello, I'm Hakim, and for our demonstration, we have simulated a small urban farm. Sensors designed to monitor soil moisture, temperature, and light levels are strategically placed approximately 17 meters away from the master painless mesh node. This node is responsible for receiving data from the slave node and transmitting the collected data to an MQTT client, which in turn publishes the information to specific topic. Our demonstration begins with the temperature sensor. Ariel will move the temperature sensor near a heat source, causing the LED to light up when the temperature reaches 29 degrees Celsius. I will then confirm whether the dashboard is receiving and displaying this data in real time. The top section of our interface serves as our dashboard, where we can monitor the current temperature status in real time. I will then verify if the dashboard accurately records this change. Next, we proceed with the light sensor. Similar to the temperature sensor, the dashboard will be our primary tool for monitoring. Ariel will cover the sensor to simulate darkness, triggering the LED to indicate the absence of light. Again, I will confirm whether the dashboard is receiving the data. Finally, we test the soil moisture sensor. For this part of the demonstration, we employ the Simple Mail Transfer Protocol (SMTP), which will be activated when the soil moisture levels are low. I will check my personal Gmail account to see if I have received the notification email. In our next demonstration, we aim to expand the scope of our project by increasing the farm's area. This expansion will showcase the scalability of our project using painless mesh technology. The new area is twice the size of the previous demonstration. For this demonstration, we'll temporarily disable the painless mesh in the middle of the broker and sensors to illustrate the data reading are not being received. Upon reactivating the painless mesh, the dashboard will immediately display the data, demonstrating the system's responsiveness. And that concludes our demonstration. Thank you.
Thank you, Hakim. Now I'll be talking about the conclusion. So now I'll be talking about our solution and the benefits of it, and how it compares to existing technologies in the world. So for our solution, actually utilize a painless mesh for our transmission of data, with the added benefit of fault tolerance. So at any point in time, if any of the M5 goes down, there will be no disruption to the data transmission. And by using painless mesh, most of our data is actually more real time. Next, we'll be also talking about how scalable and flexible it is. It's very easy for you to just implement new things into the architecture of the whole urban farming solution that we have right here. So if you actually need to add in more sensors or more like let's say automatic irrigation system, you can just add it in. It's just very simple plug and play right there. And if you need more coverage, you just add in more M5 sticks. It's just that easy. And our solution is also very eco-friendly and sustainable due to the fact that we're actually using low energy communication such as BLE. So most of the sensors that we're actually using also doesn't require much power. So it's actually very much aligning with the sustainability goals. Which brings me to the next point. It's actually very cost effective. So most of the sensors are actually very affordable. And for a large scale project as such, it's also very easy for you to just buy more of the M5 sticks. It's just more accessible in general. All these things are actually very accessible. So it's actually very cost effective. And you can actually easily modify this to fit your other needs for other solutions, such as could be used for patient monitoring. If we change it into a situation where it's actually used for a wearable on patients and just transmit data to a central hub and all that stuff. It's actually very easy to modify if you want to use it for another kind of solution apart from urban farming. Thank you.